Hello, and welcome back to another IB Math Speedrun with me, Vince. Today we're going to be going through the chapter 7.2 of the textbook, so let's jump right in. So, chapter 7.2 is all about exponents and logarithms. So, first we need to go over what an exponent is. And in case you're not familiar, an exponent is a number, it is a number that is being, it's best to explain this in this form. If we have a number a to the power of m is the exponent, and a is the base in this case, then this is equal to a times m times. So yeah, a is called the base and m is called the exponent. So m is the number of times we're multiplying a by itself. And we can also call it the index or the power. There's lots of different names for it. And so there are lots of applications of exponents, some of which we will be exploring in this chapter. So let's jump right into some questions, because there's not much else to say about exponents yet. Oh, it's a bit slow today. So the first thing we need to tackle is, I'll just do the odd problems. So we have first, find the value of these expressions. And the first expression we need to find the value of is 81 to the 3/4. So you might be asking, well, I've never covered fractional exponents yet. Well, this is pretty simple, and this is how we would do it. So this is equal to 81 to the 1/4 to the power of 3. This is how I normally think of them. Separate the numerator and the denominator in this kind of form, and then we can solve it. And we can do that because exponents have several properties, which I'll go over right now. So first of all, if you have an exponent times another, something raised to the power of m times something raised to the power of n, if they have the same base, this is equal to a times m plus n to the power of m plus n. Similarly, if we have a to the m over a to the n, this is equal to a to the m minus n. Finally, if we have a to the m to the power of n, this is equal to a to the m times n. So these are the three properties you need to know. Anyways, going back to our question, this is why we can separate this into these two and then solve. So 81 to the power of 1/4 is the same as saying 4 square root 81, which is equal to 3. Then 3 to the power of 3 is equal to 27. So that is the answer. Okay, the next one we need to solve is 32 over 243 to the 2/5. And so another useful property is that we can split exponents in fractions to both the top and bottom. So this is equal to 32 to the 2/5 over 243 to the 2/5. So 32 to the 2/5, again, you could separate them, but in this case, it's 32. The fifth root of 32 squared, fifth root of 32 is 2, so 2 squared is 4. Fifth root of 243 is 3, 3 squared is 9, so this will be 4 over 9. Okay, next. We need to show that each of these equalities is true. First, a to the negative 2 plus 2a to the negative 1 plus 1 over a to the negative 3 is equal to a times a plus 1 squared. So this looks pretty simple. At the top here, we can factorize that into a to the negative 1 plus 1. Actually, no. A better way to do this is to multiply the top and bottom by a cubed. So what this transforms everything into is this transforms this into a. This is 2a to the 2, and this is a cubed. So if we can do that because it's effectively removing this denominator. Oh, I've wiped it. And so if we factorize this, this will become 8 because this is a times a squared plus 2a plus 8 plus 1, and so we can factorize it into that. So that's why it's true. Next question, we need to simplify the square root of 9y cubed over the square root of 8, the cube root of 8y squared. We need to simplify it, and we need to use it to show that when y is equal to 64, this expression is equal to 48. Okay, so let's simplify this first. We can, sorry, not 8. This is only the cube root. So in order to simplify this, we can break this apart a little. This is equal to 3 times the square root of y cubed. So this is 3y to the 3 halves over the cube root of 8 is 2, and then we have 2y to the 3 halves. Oh, sorry, to the 2/3 here. So we can simplify this again. So this will be equal to 3 halves of 3 halves of y to the power of 3 halves minus 2/3. So this is equal to 9 over 6 minus 4 over 6. So this is 3 halves y to the 5/6. So if we plug in y as 64, we have 3 halves times y to the 5/6. 64, the 6th root of 64 is 2. 2 to the 5 is 32. So we have 3 halves of 32, which is equal to 48. Excuse me. So that's why this is correct. Okay, on to the next one. We have simplify the following. 21 times 3 to the 4n minus 1 is minus 7 times 9 to the 2n. Okay, so this one is pretty simple to simplify because we know 21 is actually equal to 3 times 7. Since we're multiplying 3 to the, well, this is technically 3 to the 1, the 3 to the 4n minus 1, this becomes 3 to the 4n. So this is 7 times 3 to the 4n minus 7 times 9 to the 2n. But the thing is, 7 times 9 to the 2n is equal to 7 times 3 squared to the 2n. And if we multiply these two, that's equal to 7 times 3 to the 4n as well. So this should simply be equal to 0, I believe. Let's just check that that's correct. Where are we? Yep, that's correct. It's simply equal to 0, since they both cancel out. They're both the same. Okay, next we have solve the following equations. First, 2 to the 3x minus 2 to the 7x minus 2 is equal to 0. And to solve this equation, it's pretty simple. We have 2 to the 3x is equal to 2 to the 7x minus 2. And so therefore, 3x is equal to 7x minus 2. It's pretty logical. So we have 2 is equal to 4x. So x is equal to 1/2. Yep. Next, we need to solve 9 to the x plus 9 is equal to 10 times 3 to the x. Okay. How are we going to do this one? I guess we could factor this into 9 times 9x minus 1 is equal to 10 times 3 to the x. Or no. This is what we're going to do. Because here we have 9 to the 3x is equal to 3 to the 2x plus 3 squared. And this is equal to 10 times 3 to the x. So we can actually factor this equation because we know that this is equal to 3 to the x. This is minus, right? So 3 to the x minus 1 times 3 to the x minus 9. Since negative 1 times negative 9 is 9, and yeah. If we negative 1 times negative 3, negative 9 times negative 3 is negative 10/3, because we transfer this over to the side. So we have 3x is equal to 1, so therefore x equals 0. Or 3 to the x equals 9. So therefore x is equal to 2. So these should be our two solutions to this equation. Yeah. So next problem, it's a word problem. So we have a house bought for 300,000 in 2000 was sold for 500,000 in 2010. Determine the annual rate of appreciation of the house to the nearest percent. Okay, so we know that the original price is 300,000, and then if we multiply this by the interest rate, which we'll call z, why not? No, let's call it x. So 3,000x raised to 10, since each year we multiply it by the interest rate. This is a pretty neat trick for finance. So if we have the annual interest rate, we simply need to raise it to the power of the number of years to get the final interest rate, if it's compound interest, and it's sold for 500,000 in 2010. So we have x to the 10 is equal to 5/3. So x should be equal to the 10th root of 5/3. So we can get that. My calculator does not have 10th root. Okay, so I'm gonna have to go to Google to get the 10th root. So we get, I guess, no, wait, I can just raise 5/3 to the negative 10. That's a pretty hacky trick. So, wait, that did not work as intended. Sorry, 1/10. I need to raise it to 1/10. 5/3 the 0.1. So we get an interest rate of 1.05 to the nearest percent if you punch that into your calculator. So it appreciated by around 5% a year. Next, we have 9 Paloma. Why do you do this to me? Paloma invests $2,000 at Superior Bank, which offers 6% interest rate compounded quarterly. Provided she leaves the money in the bank for 10 years. Her sister, Concita, invests $1,500 at Best Bank, which offers 6% interest compounded annually, and 500 at Better Bank, which offers 3% interest compounded monthly, provided the money is fixed for 10 years. Calculate the value of each sister's investment at the end of 10 years. Okay, so let's do Paloma first. 6% interest rate, 6% interest compounded quarterly. I'm going to assume that's 6% interest per annum compounded quarterly. So that's equal to 2,000 times 1.5, since if you have 6% over the entire year, you would have 1.5 in each quarter. It's the power of 10. Sorry, what is 1.015? I mean 0.015. Actually, this is a bit tricky. So it's compounded quarterly, so we have to raise it to the power of 4, so we get the 6% plus extra interest to the power of 10. So you might notice this is equal to 2,000 to the times 1.015 to the power of 40. So the final investment should be equal to $3,628. Next, we need to, this is two separate ones added together. So first is 1,500 times 1.06 to the power of 10. And we need to add to it 500 times 3% interest compounded monthly. So we have to divide 3 by 12. So this is 0.25. So this is 1.0025 to the power of 12 for the 12 months, to the power of 10 for the 10 years. So it's going to add up to a lot. So first, 1,500 times 1.06 to the power of 10 is equal to 2686. And we need to add to that 500 times 1.0025 to the power of 120, which is 674.7. So that plus 2686 is equal to around $3,361, I think, by my calculations. So actually, the second sister is a bit better off. Oh, okay, that's weird. So they're actually doing 6% interest compounded. What? Why would? Okay. This is very weird. I have a feeling that this is actually 6% interest. So this is actually 1.06 here, which is a silly amount. And then this is 1.03. What kind of bank would give that kind of interest rate? Anyways, let's try again. 2,000 times 1.06 to the power of 40. And yeah, so they actually assume they give 6% interest a quarter. Okay, so this would be $20,571. Now this amount remains the same. This should be 2686. It's just this bottom amount that will change by a lot. So we have 500 times 1.03 to the power of 120. And this ends up with 17,355. So if we add 2686 to this, we get the full amount, 20,041. So the first sister is slightly better off, but dang, that's a very high interest rate. Anyways, yeah, so that is all for the speedrun. I hope you enjoyed, and I hope to see you in the next one.